Greetings, mathophiles. Welcome to a video on part 2 of the Fundamental Theorem of Calculus. You're going to get the most out of this video if you know something about definite integrals and something about part 1 of the Fundamental Theorem. And I will place some links in this video's description to some background if you should need that before you proceed with this topic. When we looked at the first part of the Fundamental Theorem, we saw that it was possible to create what one might call an area function. You could take a look at the region bounded by the x-axis and the graph of some function on some closed interval, and the function and the endpoints of the interval would define some area. If you fixed one of the endpoints, then basically the area, and you fix the function, then basically the area ends up depending on the other endpoint. You'll see on your screen the example we used in the part 1 video. We have the squaring function on closed 1,4, and we have right now a midpoint Riemann sum highlighted graphically with 4 subintervals. And if we significantly increase the number of subintervals, as you will be aware if you have some background, or as you probably will find very intuitive if you don't, we get a better and better approximation. And then what happens is we can vary the right endpoint of this interval. And for any choice of that right endpoint, we get a different area. And so this is what I mean by an area function. You tell me the right endpoint of this interval. I'll tell you if I have the skills or if the function's not too difficult, I'll tell you the area. And what we're interested in today is what happens if you try to differentiate that area function. And if you know something about part 1, you can probably make a pretty good guess, but we need to sort of qualify some things that have to do with that. So that's our task today. So we're going to look a little formally at what we just saw on the Desmos screen. We said that the area was some function of x. I suppose I could call it a of x. But this is going to be equal to the integral from 0 to some x under the squaring function. And I'm going to use a different variable name for the integrand because I don't want to confuse two different uses of one variable. If I call that x as well, I would be using x as the independent variable in the area function and also as the variable of integration. And while it might not be technically a violation, it can certainly be confusing. It ends up not mattering because, as you'll see, we plug things in for these t's. And by the time we're done, it sort of doesn't matter what we call them. So the question we want to ask is, what is f prime of x? If this is f, what is the derivative with respect to x of the integral from 0 to x of t squared dt? Well, we know from fundamental theorem part 1 that if the integrand is continuous, and it is, all we have to do is take its antiderivative and then plug in the upper limit, plug in the lower limit, and subtract. So big F prime is the derivative of the thing you get when you do that, because the thing you get when you do that is equal to this definite integral. So the antiderivative of t squared is t cubed over 3, and this is from 0 to x. So we are differentiating, by the time we plug in and subtract, x cubed over 3 minus 0 cubed over 3. And I differentiate x cubed over 3, I get x squared. I differentiate this constant 0, I of course get 0. And so the derivative is x squared. And it should surprise no one that, except for the variable name, that's a match with the integrand. Let's take a look at what happens if you attempt this in a sort of generic situation. So let's ask ourselves, what happens if you ask, what is the derivative with respect to x of the integral from some constant to x of some function f of t dt? Well, if little f is continuous, so let's assume it is, then the fundamental theorem, part 1, applies. And so provided that f has an antiderivative, and we'll talk about that a little bit more momentarily, Provided that little f has an antiderivative, what we're asking is, what is the derivative with respect to x of big F of x minus big F of a? So we're letting big F represent the antiderivative of little f. Well, that is big F prime of x minus 0, since f of a is a constant. But big F prime of x, we said moments ago, was little f of x. And so the derivative of a function defined in this fashion ought to just be, assuming the right conditions are in place, ought to just be whatever the integrand was. Let's formalize that into a statement of the second fundamental theorem. So, fundamental theorem of calculus part 2, similar in spirit to part 1 in that it expresses a type of inverse relationship between differentiation and integration, but comes at it from a different direction. So let little f be continuous on some interval I, and let a belong to I. If you define some function f of x, big F of x, to be the integral from a constant to x of f of t dt, then big F prime of x is just little f of x. Or equivalently, approached with a slightly different notation, the derivative with respect to x of the integral from a to x of little f of t dt is little f of x. If you take the time to go through a proof of the fundamental theorem part 2, you'll find that it's guaranteed that if f is continuous, it has an antiderivative. So that's the thing we're assuming. We'll round out the video with 3 examples that will illustrate fundamental theorem part 2 sort of in daily use. And the first asks, what is the derivative with respect to x of the integral from 0 to x of cosine t over the square root of 1 minus t dt? We should check the conditions. Is this function continuous? Yes, it is. Cosine is continuous. Square root of 1 minus t is continuous everywhere the argument of that square root is positive, which is an interval that includes 0, so we're okay. So by the fundamental theorem part 2, this is just the cosine of x over the square root of 1 minus x. It's just that simple. You're sticking x's in place of t's, or whatever the independent variable is in place of whatever the variable of integration is. But we did need to check the conditions. That's important. And we should actually note where this is good and where it's not. So we need 1 minus t to be strictly positive, which means we need t to be less than 1. But for t less than 1, this is the derivative of this function. We might ask, because this comes up, what happens if those positions are reversed? What happens if the constant is above and the independent variable is below? Let's keep everything else the same. Well, if you know a little something about definite integrals, or if you know a little something about fundamental theorem part 1, you know that all that the reversal of the positions of the limits of integration does is change the sign, sign, of the result. So if I differentiate the opposite of something, I should get the opposite of the derivative of the something. So all I need to do is slap a negative sign in front of the result we just got. That's an easy thing to miss in the heat of battle, but you want to try to attend to that. You want to try to notice situations where those positions are reversed from the way you see them stated in the theorem. And finally, what if you're asked for a second derivative? Second derivative of integral 1 to x of 2 to the t dt. Well, second derivatives are derivatives of first derivatives, right? So what is the derivative with respect to x of the first derivative of this function defined by this integral? And that, according to fundamental theorem part 2, is 2 to the x. And then we just go again. So in situations where you ask for a higher order derivative, typically the fundamental theorem is going to give you a first derivative, and then from there on out, you're back in familiar differentiation territory. I hope this has been a helpful introduction to the fundamental theorem part 2. There is a complication that we haven't addressed, and that is what happens if you have a function of x in this position. Still should be possible to get a derivative in situations where a derivative exists. We're going to save that for another time. It's on the list of future topics. So until then, happy mathing.